Here, today let's try to solve this problem called number of balanced integers in a range. So in this problem, you are given two integers, low and high. An integer is called balanced if it satisfies both of the following conditions. First, it must contain at least two digits. Second, the sum of digits at even position is equal to the sum of digits at odd position. So the leftmost digit has position 1, and we need to return an integer representing the number of balanced integers in the range low and high, and both are inclusive. So let's take a look at the first example. It says low equal 1 and high equals 100, and we should return 9 because in this range from 1 to 100, 11 is balanced because, like, as you can see, 1 and 1. So you see this is the, I think this is the even position. So this is the odd position. So let me think. So odd is 1, and then even is 1 because 1 equals 1. So this is valid, and also 2 is the same story, and 3 is also the same story. So everything listed here will be balanced, and we have 9 of them, so we just return 9. And 120 and 129, we should return 1 because only 121 is balanced. Let's take a look at 121. So 121, in this case, I think the first one and the third one is on the odd position, so it's 1 and 1, and an even position is 2. So 1 plus 1 is 2, and 2 is just 2, so 2 equals 2. So that's why this number is balanced. So this one, for example, 122 is not balanced. Sorry. 122 is not balanced because, so here we need to change from 1 to 2, and 1 plus 2 is 3. 3 does not equal to 2, so that's why 122, for example, is not balanced. So you can do that for any other number, and you will know that only 121 is balanced. That's why in this range we just return 1 here. And the same story for 1, 2, 3, 4 as well, because 1, 2, 3, 4 only contains one number, and 1, 2, 3, 4, this number is not a balanced number. So yeah, so that's pretty much all for the problem description, and let's think about how can we actually solve the problem. So whenever you see a problem like this, it is probably the most useful way is to think about how can we simplify the problem. So right now we want to know, for example, we want to know like count balanced, low to high. We want to get the number of balanced numbers in the range of low to high. So usually we can simplify the problem like in the following. We just need to solve, for example, we just need to think about how can we solve x. Number of balanced numbers less than or equal to x. And once we know this, and then count balanced low and high is just solve high minus solve low minus 1. So this would give us the answer, and then we only need to think about how can we solve this function, which is to return the number of balanced numbers given x, which is in my opinion significantly easier to handle. So how can we solve this? Let me copy this here. How can we solve this problem? So we can think in maybe in a DFS way first, and we can kind of improve that later to iterative DP. So why do I think of DFS? It's mainly because of, well, the input number is like 10 to the power of 15. It seems like a really large number. If we want to handle them one by one, that's going to be very large. But if we treat it as like a string, it will be just a string of size 15. So if we have a string of size 15, we just need to do the DFS. Used DFS to determine which for each position what characters. In this case, character is the digit can be placed here. So what do we know? So our target is that sum will equal 0. I mean, the digit sum will equal 0. So what I mean by that is when in like odd position, we will do like sum minus digit, and when in even position, we do like sum plus equals digit. So if that's how we're gonna handle the digit sum, then by the end of like iterating the string here, like because as I mentioned before, I'm gonna treat the number as string. So if we have like a number like this, and we just treat it like a string, then we're gonna start from the first character, and then the second character, the third, and then the fourth, then the last. So whenever we do the DFS and then reach the last character, and our target is if the sum is 0, and then we just return 1. If it is not, then we return 0, basically. Yeah, that's mainly the idea, how you're gonna write the recursive call. And the second observation is that we actually don't necessarily need to group the numbers by counting from the left. That's what I'm trying to say. So what I'm trying to say is that, let's say 1, 2, 3, 4, 5, 6, and then you can see the odd group will be 1, 3, and 5, right? 1, 3, and 5, and the even group will be 2, 4, and 6. So what if we add one more number here, and the whole thing will change? See, so this even will become here, and this will become odd actually, and this will become even, if that makes sense. So we don't really need to care about whether the position is even or odd, because when we add one more number to the left, and the even or odd will be changed. So it is better for us to calculate the group or based on the size of the right, if that makes sense. So let's say we already have this string which is asked, and the way that we're going to count the group, instead of just position mach2, we're going to use like s.size minus position mach2. That will determine the group. And because if we do that in that way, the group is gonna stay the same if like the length is smaller. And yeah, but that's pretty much the whole idea of the implementation. So to reiterate, we're gonna use our recursive, and then recursive program, recursive like DFS to solve that. And second is the main point. The second main point is to treat the x as a string, and third is to calculate group based on s dot size minus post of 2. So the recursive call here, let me expand. It will be, so what information do we need? Of course, we need the post, because as I mentioned before, we are treating number like a string. So we need to iterate the string like from left to right, for example, and then this pointer will be post. And what our information do we need? We need some, because depending of the position, if it is like, for example, if it is group, we will have like, because we do Mach 2 here, we will either be group 0 or group 1. It doesn't matter. If group 0, if there is group 0, then some minus digit. Else it has to be group 1, and it's just sum plus equals digit. So in here, so we need to consider this sum, and also we need to consider another variable. Let's call it type. It is pretty common. Pretty common in DP. So basically, this type variable control the options we can pick from the digit. Well, what I mean by that is like I'm gonna iterate every number in the range, but what digits can I pick? For example, I can pick like 0 here, I can pick 1 here. So if I pick 0 here, then the next position I can actually pick 0, I can pick 1, I can pick 2, I can pick 4, I can pick 5. But if I pick 1 here, then I can only pick 0 or 1. Because if I pick 2, I'm considering something that is over my limit. So that's why if this type is true, then it means I can only pick like if type is true, then we can only pick the digit from, if type, we can only pick from 0 all the way to S position. So S is the number in string format. If it is not else, then we can basically pick anything, which is from 0 to 9, yeah, for this current digit. So we're gonna do that. So this should be enough for the DFS parameter. Let's think about the base case. So if position, like when it reach like the end, like s dot size, and we just return 1 if like sum is 0, else 0, because when the sum is 0, it means that we have reached all the digit. And then the odd group is actually equal to the even group. That's why we have this sum 0. And then we just and otherwise we'll just iterate all digit for all possible digit based on type. Digit D. So if like the group is 0, then we do the like DFS. So answer plus equals to DFS pose plus 1, and then sum. Let's say if it is group 0, then I do minus digit, so minus D, and then type. Type is like if it is currently is type, and the current is type, and also the D is equals to s dot pose basically. So if it is currently is type, so first of all, whether it is type is because it just means that we cannot pick any digit as we wish basically. So the only time that the next gonna be type is that if previous is type, because if previous is not type, for example, it's just here, then of course we can choose whatever we want. It doesn't really matter. So the only time is gonna kind of inherit the type is that the previous is type, and now I'm also the exact same digit as the limit, the limit which will be as post. So if that's the case, then the type is going to be true, otherwise it's going to be forced. If it is not, if the group is not 0, then we just like do a very similar thing, but we do like sum plus D. Yeah, that's like the basic idea of the recursive DP. And yeah, that's pretty much all. And then we can kind of memorize it, the recursive call. So the total time complexity will be like, so since like the number can be 10 to the power of 15, so we could assume the S length is 15. So it will be like OS length times the sum. The sum, like the sum will be something like, because the digit can go up to 9, so we just assume it's 10. So it will be like 10 times 15, which is like 150, something like that, and type will be 2. So it will be something around like S length time 300. This S length, maybe I can just log x. So this is for solve x, which I have mentioned before, just to calculate the number of balanced number less than or equals to x. This will be log x. Because we do it twice, once for let me see, once for high and once for low -1. So that's why it will be like 2 times this, and this will be the total time complexity. If we do the memorization, of course. Now, right now, this just the DFS, it won't have the memorization. So this will be exponential if I just leave it as it is. But you get the idea, and we will try to implement that later in code, and you can see how can we actually improve that to iterative DP as well. Yeah, but that's pretty much all for the intuition for this problem. Let's think about how can we actually implement that. Okay, so let's get started. As we discussed before, instead of calculating the range between low and high, we're going to do in the following. We're going to return solve high minus solve low plus 1. So this solve basically it's just trying to solve the same problem, but in a similar like definition. Return number of balanced number of balanced numbers less or equal to x. So by that definition, you will understand why solve high minus solve low minus 1 will work. So I'm not going to explain too much to that. So how can we solve this subproblem? So again, as I mentioned before, we need to treat this number as string first, and then for each position, then we will use DFS to determine what digit we're going to place on that position. So first we're going to turn this whole number to a string first. In C++, we can just use to_string, and then we kind of like initialize the size, and then we are going to do DFS. So this DFS is, I'm going to use lambda. So this DFS is going to return a long at the end, and it's going to accept, again, we already discussed, the first one is going to be like DFS. The first one is going to be position. The second one is going to be sum. The third parameter is going to be type. So that's why we need 3 integer parameter here. So I'm going to write int. And it's called this function DFS. So DFS just going to, this will, like in C++, this will have access to S automatically if I add this address here. So again, we will have post, we will have sum, we will have type. So let's first handle the base case. If we reach the S length, so it means that we already reached the end. We just want to know if the sum equals to 0. If it is 0, and then we just return 1, but I need to change it to long because 1 by itself is just an integer, so I have to change it to long in C++. And then if it's not reaching the end, we are going to, first of all, we're going to know what are the options we can pick. So based on type, so the maximum digit that you can take, let's call it mx, standing for max. So if it is tight, for maybe let's start with a simple case. If it is not tight, and we can actually end at 9. And if it is tight, then the limit that we can choose is the current position of the string, because we are treating the number as a string right now, so it should make things so much easier. And then this long will be answer. So this answer will just return the number of balanced number in this position, and with this current sum, and also whether currently is tight or not. And finally, you're going to return the answer. But let's just think of whether we're going to add or not. Should add equals to s length minus post mock 2. This will determine whether we should add to the sum or subtract to the sum. So then we can just loop from this 0, ch less than or equals mx, ch plus plus. So the next sum, the next digit sum, if it is that, and it will be sum plus, we cannot just plus ch because ch right now is character. We need to change that to digit value first. So I'm just going to write ch minus the character of 0, because like if 0 character minus 0 character will be 0, if 1 character minus 0 character will be 1, so on and so forth. This will give us the digit value in integer. So if it should add, then we add it to the sum. If it is not, then we do the subtract. And then after we know the next sum, we just do the DFS here. So we're just going to do the next position. We move to the next position because we have already considered this position to use the current CH as the digit. We also know the next sum as well. And tight, again, tight, I think I already explained it before. But the only time it's going to stay tight is that it's currently is already tight. And also we are choosing the maximum here. Yeah. And after that's done, and we can just return the answer here. And then finally, the total number of what we're trying to solve here is just return DFS 0. We're going to start the position at 0. The sum is currently at 0 as well. And then tight currently is true. And then we're going to try to run the sample test cases to see if it makes sense. Yeah, it makes sense, but apparently this won't pass because we haven't done any memoization here. And also there's another thing. If we want to do DP here, you will notice this sum can be negative. So that's why there's one small trick that we can do that might seem not as intuitive. Basically, I want to add based. Let's say 100. I pick 100 because we know before that the requirement is 10 to the power 15. So like, what is the minimum number digit sum we can reach is basically like so for example, the even group could be negative, could be making the sum smaller, so we have 7 of them. So assume that 7 of them is like or 9, and all the other like number are 0 in the odd group. So it will be like, I should just take it at 100. So let's assume this is 100. So in the worst case scenario, it will never go less than or equal to like negative 100. So I just add the base. So now instead of checking if it is 0, I'm going to check if it is equal to base. And obviously, I'm not going to start from 0 now. I'm going to start from base now. So let me run again. It should give us the exact same result as before. Yeah, it gives us the exact same result as before. So now let's think about how can we optimize this recursive call. So again, it's like doing this kind of stuff is pretty straightforward if you have done it several times before. Whenever you want to convert some DFS call to iterative DP, the first thing is to look at how many parameter you use here. So here we use 3 parameter. So I'm just going to write a DP function, DP array, which has 3 dimensions. But before that, we know we use 3 parameter here. So that's why we know that we need to loop 3 times. The first is the post. The second is the sum. And the third one is whether tight or not. And then after we know that, we can just copy the O function body directly to the loop body. And then we do return here. So we do return here. We need to change it to DP post sum tight equals here. And because we do return previously, we need to add continue here. And then here Whenever we do DFS, we need to change them to DP. So whenever we do return, we need to change the return to the current like DP. So that should be it. Let me think. So then the next thing is to create this kind of DP array. So we know this position can go from, you know, from, you see here, it can go from S length. So the first dimension is S length. And the sum, let's think about the sum. The sum can be, let me think. Again, we have 15 digit because like the high can be 10 to the power 15. So we basically have 15 digit. So 15, like let's assume they are all 9. It will give us around 150, but I'm just being generous here. I just give the second dimension to be 200. And for the height, it is just a Boolean value 0 or 1. So now we know the dimension. We are just going to write it down here. So it will be a factor of factor. So the first factor will be the position, the second factor will be the sum, the third will be just the type. So this one, close here, close this one, and then we finally have that. Okay, so we call it DP. So the first dimension is length plus 1, and then the next one is vector array long 2, and then we have 200 here. And yeah, that's basically it. That is the definition of the DP like array we're going to initialize. So let us think about how we access the DP memory. So this one is actually accessing post plus 1. Okay, I'm missing some equal sign here. So this is accessing the post plus 1. So as long as we are visiting from the end from the largest to the smallest, then we should be good. Okay, because every time we just visit the things that is post plus 1. So as long as the whole post plus 1 is ready, then we can safely use this recursive like DP or DP array. So this one we will need to make sure that when we doing post sum type, post plus 1 next sum type, whatever should be ready. Okay. So DP, so that's why we need to start from the largest. Post less than or equal to 0, close minus minus, and then sum. As I mentioned before, we're just going to use 200 as the sum plus plus. So type is 0, type can be 2, can be 0 or 1, so it's less than 2, so type plus plus. So here we need to do another checking. So basically this next sum, if it is reaching 0, so normally it will never reach 0 as I mentioned because we have a base of 100. There's no way we can reach 0 if we do recursively. But if we are doing iteratively, when we do this 0, we are actually possible to reach. Sorry, we're actually possible to reach like negative here. So, but they are not going to return us any value. So if this next sum is less than 0, or next sum is greater or equals to 200, then sorry, maybe I just put it in this way. So it will be 0, less than 0, or is greater than or equal to 200. Just let me type it here. So if that's the case, then we will just return 0. Otherwise, we will actually go to visit the DP value there. Okay. So yeah, that's pretty much it. And then eventually we are doing like DFS 0 and then base 1. We can now do the DP post. Sorry, it's not post, it's 0, and then based, and then 1. And this is like the whole translation from the DFS to the DP. So right now that's done. Let us just comment out this part. And then let me remove these extra spaces. Let me try to submit. Let me try to run code again. So the sample test case passed. Let's try to submit. So it's accepted. And well, before we end the video, let me just scroll back here. You can see that because we're always doing this post plus 1, we can actually kind of make the memory even more efficient by doing something like DP plus 1. So basically, what I'm trying to say is that we don't actually need to have as length number of like 200 pairs here. We just need 2. So yeah, so this will make the memory more efficient. Maybe I will just let me write that because it's not that difficult to write. So this is vector array long 2. Let's go here, and then we have DP, post plus 1. So this post plus 1 is the only thing that we reference. We don't have post plus 2 here. There's nothing post plus 3, so we just need 1. That's what I'm trying to say. So we have this 200, and we also have this. We need the current DP post. So this DP post will be here, will be 200 as well. So right now, instead of doing DP post, we do DP underscore post for the current position. And this, instead of doing DP post plus 1, we just need to do DP underscore post plus 1. And here, similar, we don't do DP post, we do DP underscore post. And finally, we reach DP 0 and base 1, and then that's what we do previously. And let's think about it. The last one we access is 0, so it's fine to use either actually. We just DP post here, and for each for each one is done, I need to know the plus 1. So right now I'm starting from the largest one. So whenever this one is ready, I want to let the next DP post to know that I am the next one that you're gonna reference here. So then I will do post minus minus, and the post minus minus will do whenever you do the post plus 1 reference, it will referencing the current DP post. If that makes sense, it's not very complicated. maybe I'm not so good at explaining that, but you get the idea. So once we have that, and then we can just simply comment this part out. We don't need this large data structure. We just need 200 DP array. Let me try one again. Okay, let me try to submit. Okay, accepted. And let me scroll back again. So for the time complexity, is going to be time O log high to the power of 2. So why? Is because first we're going to change the number to a string. So the string length by itself will be log x. So this log x, you can see we do another like sum. So where is sum coming from? This sum is actually coming from, so basically you can imagine how many digits are there. So there are log x digits there, and then each one can be 9, right? So I'm just treated as 10. So basically this is constant, by the way. So that's why this one is log x. This one is also log x. It's more like log x times 10. So but 10 is the constant, so I just treat it as log x. So this is log x. This is log x for the time complexity. And this is just 2. I'm going to ignore that because that is constant as well. And so for state complexity, it is just this one, 200. So as I just discussed before, 200 is just log x. So this one, I'm just going to use log high because high is always larger than low. Yeah, actually the whole thing it would be 2 times as well, but because we have to do it for the low -1, but you get the idea because 2 times is also a constant, so I'm gonna ignore that. Yeah, so that's pretty much all. I hope that makes it clear. Let me know if there's any question, and I'll see you in the next video. Bye.